Sounds good.
Okay, cool. Thank you for the introduction, Tom, and also thank you for giving me the opportunity to present our work here. Today, I will give an overview of some projects at Bosch that are mainly in the field of hydrogen boilers, and this is a collaborative work with a bunch of people, and I will not go through the whole list, but thank you all for the great collaboration that we have so far. And before I go into the technical part, I wanted to show a few slides about the company itself that I think I was showing. And I will start here with the guiding principle of the company, which is invented for life. And that's also in line with the vision of our founder, Robert Bosch. And this is something that you can really see in the company working here. Bosch is also over 90% owned by a foundation, the Bosch Foundation, and they get all their funding through the Bosch GmbH. So we give a lot of things back also to the community. Bosch consists of mainly 4 business sectors: mobility solutions, industrial technology, energy and building technology, and consumer goods. And here you can see the revenues that the different sectors make. And what I like a lot is that Bosch gives a substantial amount of this revenue back into the research and development. Sorry that those pictures do not render correctly here. That's a little hiccup between Mac and Windows, I guess. And yeah, so this is an overview about corporate research and development. There are over roughly 6 billion euros invested in research and development. We have over 70,000 associates working in R&D, and over almost half of them are software developers. And we have roughly 130 research and development locations worldwide. Another highlight that I think is worth showing is that last year Bosch achieved CO2 neutrality at more than 400 locations, and was the first major industrial company to go climate neutral. And we also invest a substantial amount in climate protection. Okay, so now I will introduce hydrogen ready gas boilers. And the boiler that you can see on the next slide here, sorry, I have a quite large latency when I switch the slides. Okay, so this is so-called hydrogen ready boiler that is produced by a Bosch brand called Wooster in the UK. And we are looking into hydrogen, of course, because it's a carbon neutral fuel. So when you burn it, there are no CO2 emissions. And you probably know that hydrogen can be manufactured as a renewable energy source, for example, through electrolysis. So that's the long-term goal, that we use solar or other renewable energy sources to generate hydrogen, and then we will not have any CO2 emissions. However, I think it's also important to say that at the moment, still nearly all commercially available hydrogen comes from natural gas. So what you can do is, during this process, when you generate hydrogen from methane, is to capture CO2 and store it somewhere, which might also be controversial. But it's also important to understand that we will not have clean hydrogen next year or something, but there will be a transition. And for the customer, it's important that he doesn't have to buy a new appliance in a few years if he has to buy one now. So these hydrogen ready boilers can run on traditional natural gas, but you can also run them on pure hydrogen or on a blend. So sorry, but I cannot oh, there it goes. So these boilers are
just be next, and then Juan can flip for you. Yeah.
Okay, thank you. Yeah, that's good. So therefore, those boilers are a key to enable the conversion of the gas distribution networks from natural gas to hydrogen. Okay, next, please. Okay, so here you see the backside of such a boiler, and the air enters this boiler through this air pipe. The fuel comes in through this fuel valve here, around right here. And then a double intake Venturi is used to mix air and fuel. So we try to have a most homogeneous mixture there before the gas mixture goes through the burner, which is used to stabilize the flame. And then in the heat exchanger, heat is exchanged from the hot combustion gases to the water that we want to heat up. And we apply SU2 to those three components here. And in the double intake Venturi, we have a cold flow, so there are no reactions going on. The flow is turbulent. And what's the most important to model here is really the mixing of fuel and air. Then in the burner, we have a reactive flow where most of the chemical turnover happens. It's a laminar flow, and we have a mild heat loss to the burner itself. And what we want to predict here and optimize in the end is the flame stabilization process, and of course also pressure loss, which is something we need to always take into account. And then in the heat exchanger, most of the chemical turnover has happened, but the flow might not be in perfect equilibrium yet. And depending on the cooling, emissions are formed differently. So this is what we do when we optimize the heat exchanger here. We want to optimize the NOx formation. The flow is still laminar, but we have very strong heat loss effects here because the flow is cooled down below the boiling point, basically. Okay, next, please. Okay, so now let's take a look at the double intake Venturi. So here on the right-hand side, you can see such a Venturi, and the geometry is a little complex, but I hope you can see how the air and the fuel is fed into this Venturi, and then it mixes inside. And the work that Mark Heimgärtner will show later today is aimed on implementing accurate mixing models for the gas in this Venturi. Next, please. Yeah. And the mixing here is based on a transported scalar that we call the mixture fraction. And this is based on the passive scalar framework that we showed last year. And then the fluid properties are modeled as functions of Z. And the ongoing work on Mark's side at the moment is implementing these mixing laws. And then the next step will be to integrate this into the edge-on solver to do optimization. Another work that is focused on this Venturi is executed by Lisa Kusch and the group in Kaiserslautern. And her goal here is to optimize an average value for the mixture fraction on the outlet of this Venturi. So she uses a constant mass flow rate boundary condition on the outlet, and then only prescribes pressures on the both inlets. And then basically the total mass flow is constant, but the ratio between air mass flow and fuel mass flow varies depending on the geometry of the Venturi. And here you can see an optimization run that she already did. And she hits the target after 20 iterations really well. And at the moment, she's working on including cold mixing lookup tables. So this is some work that is done until we have the accurate fluid property models by Mark available. And she also runs multi-point optimizations here because the mixture has to be at a specific value, not only for one mass flow, but depending on the power load that the boiler runs, you have different mass flow rates, and you always want to get this average value. And she does this with the FADO framework, and they use the Rodeo package for global optimization. Okay, so here we see a slide about Tobias' work. He will talk on Wednesday at 7:25. He's also looking at the Venturi partly in his work, and he tries to optimize not only the the average value of the mixture, but he's trying to optimize for a very homogeneous mixture, because this allows cleaner combustion typically and also increases the flame stability, which is very crucial in hydrogen boilers. Toby also did a lot of work for unsteady CHT problems. And of course, conjugate heat transfer is super important in these boilers, because this in the end determines how accurate the temperature boundary conditions are for the flow, which is a key factor in the emission formation. And at the moment, he's tackling numerical issues in the scalar solver, and he works on sensitivity computation for mixing related objective functions. Okay, so this was mainly what we did for the Venturi, and now I would like to talk a little bit about the burner and the heat exchanger. And here we see a slide about Evert's work. Evert will present right after me today. And Evert is working on the hydrogen modeling that we need. And last year we showed already a flamelet model for methane. Now, when we go to hydrogen, the diffusion processes are a little bit more complex. And due to those diffusion properties of hydrogen, you can get local remixing of the gases. And we can use the mixture fraction that I already discussed earlier to model these remixing effects. That, on the other hand, then necessitates three-dimensional lookup tables. And on the right-hand side here, you can see the space that we map with the chemistry table. In black, you can see the accurate 1D simulations, and then the red surfaces here are where we discretize these solutions. And Evert will tell you a little bit more about this. And he's currently on validating the combustion model, and the next step will then be to integrate everything into the adjoint solver. Okay, so I'm running out of time, so I will speed up a little bit here. This is a geometry that we also showed last year. And what we did here was already a shape optimization to reduce the emissions in such a flame. This is still done for methane. So down here you see the distribution of carbon monoxide. And the difference now is that we can run this together with the CHT solver. So we simulate the conjugate heat transfer in the solid and only prescribe a boundary condition on this little circle here on the right. And we run these simulations with the FADO framework. Next, please. Can you skip forward, please? Yes. And at the moment, we are setting up a three-dimensional case here. We can already run the primal, but we still have some hiccups when we run the adjoint. So this is ongoing work. And then, of course, the next step is to integrate everything with the hydrogen model that Evert is developing right now. And I also wanted to mention Ole. He helped us with the multiphysics solvers a lot, and his talk is on Tuesday at 7:50. Okay, so now outlook and future topics. One topic that could be a nice topic to apply SU2 is modeling of PEM fuel cells. So on the right-hand side, you see such a fuel cell power module for large trucks. And what we will do in the second half of this year is implement a porous media model to resolve the gas diffusion layers in such a fuel cell. And then we will also work on a topology optimization framework. And then later we think about, or at the moment we are thinking about implementing a framework to incorporate machine learning models for physics modeling into SU2. And besides that modeling work, we also would like to spend some time on improving the usability and the robustness. So for example, the optimization workflow and the setup is sometimes a little bit cumbersome, and we think it could be simplified a little bit. So we will spend some time on this topic. And then also we see that our scalar solver is sometimes not the most robust solver. So we will spend some time on improving the robustness of the scalar solver. Next, please. Yeah, so here, for example, you see the source term of the progress variable, and especially in regions where we have mesh cell transitions, we see that a very small source term can show up, and that leads to inaccurate emission predictions. So this is something that we are investigating right now, and I cannot tell you where this comes from, but we are investigating this, and we'll probably try some different numerical schemes to improve the scalar robustness. And that's everything from my side. So thank you very much, all the collaborators. I look forward to the future collaborating with you. And if you want to get in touch, just shoot me an email.